There's too much phase.
I was on a Zoom call a few minutes ago and it was just fine, so I don't.
All right, so let's get started here. All right, so welcome back everyone to Vamos. We have an exciting schedule for the semester. The website is partially updated, but we'll have all the talks up there shortly. To kick things off today, we're quite happy to have Thierry Lahaye from CNRS in France. Like many successful French individuals, Thierry did his PhD in the group of Jean Dalibard and then went on to do a postdoc in Tilman Fow's group in Stuttgart. Afterwards, he became a leading member of the pioneering optical tweezer group at CNRS, a group which has demonstrated a series of landmark results in recent years, especially in the area of many-body physics with assembled arrays of Rydberg atoms. This will be the subject of his talk today. So let's welcome Thierry.
Well, so thanks, Adam, and thanks everyone for the invitation. And so it's really a great pleasure to give this seminar. So the title of my talk is Quantum Simulation in Arrays of Single Rydberg Atoms. And here you have a picture of an array of optical tweezers containing single rubidium atoms. So each little dot here that you see is the fluorescence of a single rubidium atom, and the spacing between those atoms is a few microns. And we use those arrays of single atoms to study many-body physics of spin Hamiltonians. All right, so this work is done at the Institut d'Optique in Palaiseau, so just south of Paris, in the group led by Antoine Broez. And here are the people that are working in the lab. So as you can guess, this is a rather old picture, but at least you can see the faces of the people involved. We also benefit from very useful collaborations with the theory groups of Hans-Peter Büchler in Stuttgart and Andreas Leuchli in Innsbruck. All right, so our platform for quantum simulation relies on arrays of single atoms that we trap in optical tweezers that we can arrange with pretty much arbitrary geometries. So you can see here a square lattice or a triangular lattice. We can now go to arrays with a size of more than 200 atoms. And the spacing between those atoms is a few micrometers, typically within 5 and 10 microns. And so if you do nothing and you have ground state atoms in those optical tweezers, they basically do not feel each other. So we then excite them to Rydberg levels. And in that case, you get very strong interactions, typically in the megahertz range, which means that you have some interesting dynamics occurring on microsecond timescales. And this is to be compared with the lifetime of those Rydberg levels, which is typically hundreds of microseconds. So to a pretty good approximation, you can consider that you have a closed quantum system, which is just undergoing unitary evolution. And what's maybe even more important is that those arrays of Rydberg atoms, they implement in a very, very natural way without any special engineering. They implement spin models that are relevant for condensed matter, namely the Ising model. If you just rely on boundless interactions that you have between Rydberg levels, you have this kind of sigma z term for your spin-spin interactions. Now if you, instead of using the ground state and the Rydberg state as states to encode your qubit, you use two different Rydberg states like S and P. Then you can have resonant dipole-dipole interaction, and then in terms of spins, the Hamiltonian you implement has this sigma plus sigma minus term, so this flip-flop, and this is the XY model. So the outline of my talk will be the following. I will spend a bit of time at the beginning to guide you through the various steps that we put together to create this platform. And then I will show you some examples of recent quantum simulation of spin Hamiltonians that we did basically over the last 2 years. First with Ising, and if I have time, with the resonant dipole-dipole interaction. All right, So the first ingredient that we use is the trapping of single atoms in optical tweezers. So here you have a basic sketch of the experiment where you have aspheric lenses in a vacuum chamber. They have a relatively high numerical aperture, and you can take a laser beam and focus it down to a waist of about 1 micrometer. So this is just a regular optical dipole trap, except that it's really small. And when you load cold atoms from a MOT into those optical dipole traps, the speed at which light-assisted collisions occur in those traps is very high, which means that if you have 2 atoms at the same time in the tweezers, they get expelled very, very quickly because you have those light-assisted collisions. And so this means that basically if you start from an empty trap, then at some point you will load an atom in the trap, and a bit later you may have another atom entering the trap, and then very quickly on experimental timescales, you lose both atoms. Which means you come back to the previous situation of an empty tweezers. And so this is a way to realize a single atom source, but it's non-deterministic. And at any given time, you have a 50% loading probability for your optical tweezers. So this is something you can observe in the lab by just monitoring the fluorescence that you collect with the same lenses on a camera, for example, and you have those 2 levels corresponding to no atom or 1 atom in your trap. So this is something that was actually pioneered at Institut d'Optique by Philippe Granger and his team 20 years ago. And at the time, the idea was to do quantum optics experiments. But more recently, we have started, and then of course we are not the only ones, to expand this to many traps and many atoms. And so the first thing, of course, is to create an array of such optical tweezers. In our case, we use a spatial light modulator, which is just a phase grating that you control with the computer. And depending on the phase you imprint on your trapping beam, then when you focus it down with the optical tweezer, with the lenses here, you will get basically, for instance, this kind of square lattice or triangular lattice or kagome or whatever, provided you have calculated the right phase to apply here. And if you look with your camera and observe over long times, if in each trap you can capture some atoms, you really see this nice picture. But this is an average image, because if I focus, for example, on this 10 by 10 square array here, and I just load atoms from the MOT into this array of traps, each trap has a 50% probability to be filled. And so I will get this kind of configuration here. And you see that basically you have on average 50% loading, and this is a highly disordered configuration. And of course, if you repeat the experiment several times, you will have different configurations at each shot. So this is not a good starting point for doing quantum simulation. And so the way we solve this problem is actually quite basic. The idea is just to sort the atoms one by one using a moving optical tweezers. So if you want in the end to have a nicely ordered array like this 6 by 6 square array, the idea is to start from a larger array which contains the target array, load it with about n atoms if you have 2 n traps, and then take an image, a fluorescence image, to know where the atoms are. And then what you have to do is to compute on the fly how to move the atoms from one place to the other in order to get to the final configuration. And this actually you can do pretty fast. For 50 atoms or so, you can do this in 1 millisecond or so. And then to actually move really the atoms one by one, you do this with an extra optical tweezers, which is controlled by acousto-optic deflectors. And you can also do this pretty fast, typically 1 millisecond per move, which means that in a few tens of milliseconds, you get this fully ordered array. And so when we demonstrated this 4 years ago, we were able to reach arrays with about 50 atoms. The typical filling fraction is in excess of 98%. And still the process is relatively fast. You have a rep rate of about 4 Hertz, which is of course very nice when you want to acquire statistics and so on. This is much faster than what you do with quantum gases, for example. And of course, at the same time, at Harvard and also in Korea, there were demonstrations of the same approach with slightly different technical means, but basically the same atom by atom assembly. And since then, we have extended a bit the capabilities of the platform. So one thing we demonstrated is that you can extend this to 3D structures, actually. So here are a few examples. So far, we have not used that for quantum simulation, but this is, of course, on the to-do list in the future, because I think it opens quite a few interesting prospects for quantum simulation. And a more recent improvement, which actually took place during the lockdown that we had in March and April in France. The students were stuck at home, so they had to focus on something interesting. And they really improved a lot the kind of algorithms we use to sort out the atoms and so on. And they came up with more efficient methods, which really allow us now to go to more to 200 atoms on a regular basis. And so here you have some examples in 1D and 2D. And also one thing we did is to extend the possibilities to have geometries which are not basically not just contained in a regular array. And here you have an example. For example, this is a square lattice with an edge dislocation here in the middle. And so this is also something which is quite nice if you think of studying, condensed matter problems. Having this degree of freedom is quite interesting. And also it's something, of course, which allows you to have a bit of fun. So we could, for instance, replicate this Mona Lisa thing in the lab. All right. So the next ingredient is to have interactions between those atoms. And so to do that, we excite them to Rydberg levels. So with a large principal quantum number, typically between 50 and 100. Which means that those atoms have a very large size, typically n squared times the size of ground state atoms, which means that they have exaggerated properties because they have a very large dipole moment between adjacent Rydberg levels. And also they have these very long lifetimes of hundreds of microseconds, which gets actually longer and longer when you go up in n. So in practice in the lab, to go to these Rydberg levels, we couple the ground state of our rubidium atoms with, for example, the NS state by using this kind of two-photon transition. And if you do that, you observe this nice coherent Rabi oscillation with high contrast and little damping. There is some damping, but it's relatively small. So for some experiments, you want actually to use the rich level structure of Rydberg states, and for instance, to manipulate the Rydberg levels between NS and NP. And this is something that you can do very conveniently by using just microwaves. And here you have an example of Rabi oscillation between those two levels, again, with very little damping. So just very briefly, in the experiments I will show you today, when we prepare our atoms in the array of tweezers, then to do the Rydberg excitation, we just switch off the traps for a few microseconds. And then the atoms are just basically standing still in free space. They start to fall, but they fall by a very tiny amount. But of course, at some point, the finite temperature of the atoms and so on limits the time over which you can do quantum simulation. And so one of the things we demonstrated last year is that actually you can also trap the Rydbergs by using a different type of optical tweezers, a bottle beam trap that you can create with an SLM also. And then you create a region of space where you have no light. And all around this, you have a non-zero amount of non-zero intensity of light. And so this is a trapping potential for Rydberg atom, because essentially the electron of the Rydberg atom is almost free. So it essentially experiences just the ponder-motive potential created by the laser field. And then the potential experienced by your Rydberg atom is given by this expression. And so we showed that we could actually keep Rydberg atoms trapped in these tiny optical tweezers for a time which is essentially limited by the Rydberg lifetime. So this is what you get with the trapping, and without trapping, you are actually limited to just the very beginning of this curve here. Note that this here, the scale is in milliseconds, right? So usually we just use a few microseconds for our experiments. So again, we are not using this yet for experiments, but this is just to show that there is some potential for improvements in the future. All right, so as I said, the very reason why we use Rydberg states is because they interact very strongly. So if you take two Rydberg atoms separated by distance r, they are interacting mainly via this dipole-dipole interaction here. And now the effect on the pair of atoms of this interaction depends on how you prepare the states. So if you, for example, just take twice the same Rydberg level for your two atoms, in fact, you don't have any effect at first order of this dipole-dipole interaction, but you have a second order shift, which is just the van der Waals interaction. So it's just a shift, and it scales as 1/r⁶. So it's pretty short range. And in that case of the van der Waals interaction, if you encode a spin 1/2 by saying that the ground state of your atom is spin down and the Rydberg state is a spin up, as you will see, this maps exactly onto the Ising model of condensed matter. Another way to use the interactions between Rydberg levels is to use two different Rydberg levels, like the S and P. And so, for example, if you have two atoms, the first one in S, the other in P, this is directly coupled to the state PS. And so if you encode your spins, spin up and spin down in those two Rydberg levels, basically you have a flip-flop term here between up, down, and down, up. And the coupling strength is just the dipole-dipole interaction to first order. So it's decaying as 1/r⁴. And this is this kind of flip-flop term that you have in the XY interaction. All right, so I mean, I guess the audience is entirely familiar with the Rydberg blockade, but let me just very briefly recap the concept of Rydberg blockade. So the idea is that if you have a single atom here with your ground state and Rydberg state coupled by a resonant laser with Rabi frequency omega, you will undergo the Rabi oscillations I was mentioning before. And now if you have two atoms, of course, what will happen is that if they are close enough, you have the van der Waals interaction that shifts this doubly excited state. So if you start from the collective ground state here and your laser is resonant, you can couple to this single excitation manifold here, but not to the doubly excited state. And so effectively you end up coupling just this collective ground state here to this collective excited state where you have one excitation shared among the two atoms. And this is very interesting because, of course, it's an entangled state. And this mechanism is the basis for quantum gates and so on that have been proposed 20 years ago now. And also this extends to if you have many atoms in one single blockade volume, you can create collective gates and entangled states of n atoms and so on. However, in this talk, I will be more interested in a regime where the blockade exists between our atoms, but just over a relatively short range. So I've got my array of atoms here with a lattice spacing A, and I will be in a regime where the blockade radius over which the second excitation of a Rydberg is prohibited, which is just slightly bigger, than this lattice spacing. So I have nearest neighbor blockade, but I will be able to accommodate many Rydberg atoms in the system, and therefore I have some strongly correlated quantum many-body dynamics, which, as you will see, is described by the Ising model. So all this was very basic, but this was essentially to present a bit the setup and the basic ingredients. So I don't know if there are some questions maybe at this stage.
Great. Yeah, there are a couple here. So the first is, can you comment on what's different about the improved rearrangement algorithm? Is this mainly computational, or are there other things that are going on?
Yeah, so in fact, so when we first implemented this rearrangement in 2016, we had to find a way to have an algorithm which gives us the moves that you have to do to end up in the right order, this is a difficult problem because I mean, of course, you cannot compute all the possibilities. I mean, this is just exploding exponentially. So you have to come up with you know, algorithms that are heuristic, that solve the problem, but they are maybe not the optimal solution. And the system, the algorithm we came up with was actually working pretty nicely up to 50 or 70 atoms or so. But beyond that, it started to be a bit slow. And so we came up with refined algorithms which are more efficient, but in fact, we came up with 3 different algorithms that we apply depending on the type of pattern that we want to assemble. The old algorithm we had was very versatile. It could work nicely on any pattern, but only up to, say, 70 atoms. And now we can really, I mean, I think it's fair to say that we could go to even 400 or 500 atoms before being limited now by the speed of the algorithms. And what limits us to 200 is more like, you know, technical things like laser power and optical aberrations and things like this. But
I see. Okay. Okay, so we have another question from Paul Loria, who asks, would there be an advantage to pre-cooling the atoms to the 3-dimensional motional ground state of the traps before loading into the, or while they're in the tweezers?
Yeah, so that's a good question. So I didn't mention that actually here the atoms are just loaded from the MOT, and the temperature is not very low. It's around 10 microkelvin. And actually now we have some evidence that for a good agreement with theory of our quantum simulation, actually the residual motion of the atoms is starting to play a role. And so this is on the agenda to load the atoms, move them around, and then have some Raman sideband cooling to really end up with really cold atoms, such that you can expand the time for quantum simulation before the atoms move around. But we have not done it yet. But it's actually something we're even discussing in the lab this afternoon. You know, so it's really it's a hot topic.
Got it. So maybe let me ask one more question here, and there are some more, but we can save those for the second break. Is there a disadvantage? This is from Monica. Is there a disadvantage to using the Ponder motive traps that is preventing you from using them so far? Meaning, like in the present experiments, for instance.
Okay, so I mean, the thing is, it's really something we'll be able to use in practice, because you don't need like insane amount of power, and we have shown that you can really combine this with, I mean, you can make several traps arranged with pretty much arbitrary geometries and so on. We've even shown that you can, for example, have some spin exchange, some XY interaction, while the 2 Rydberg atoms are trapped in these bottle beam traps. So this is something that I think will be used at some point. The reason why we are not using it at the moment is essentially because we are dealing mostly with Ising types of experiments at the moment. And one thing that this trap is not doing at the moment is that it's not a magic trap for the ground to Rydberg transition. At the moment, actually, the bottle beam trap is sort of repulsive for the ground state. But you can, in principle, by using different wavelengths for the trapping, you can, in principle, even be in a magic at a magic wavelength and really have a trap which is the same for the ground and the Rydberg. At this stage, it becomes a bit tricky because the wavelengths are not so convenient, and you need maybe more power and so on. But I would say that the main reason for not using it now is that essentially for the Ising experiments we are doing now, extending a lot the time over which we do those experiments is not really needed. You can crank up the interactions for a fixed simulation time, but I think for some experiments where you use the XY model, this is something which could play a role and be really actually improving the quality of the simulations.
I see. Cool. Okay, I think we can keep going here, Thierry. Thank you.
All right. So now that we have basically all the tools, what I would like to do is to show you some recent results on the quadrant simulation of spin Hamiltonians. So actually earlier this year we wrote a small review in Nature Physics together with Antoine. So where we review somehow the state of the art until 1.5 years ago or so. And so I've chosen to discuss results that are more recent and that we obtained actually over the last few months. All right, so let me start with the quantum Ising model. And so this is exactly what I was mentioning before. We have this array of atoms. Each atom has a ground state and the Rydberg level. So this is spin down, spin up. And I shine on the array of atoms a global laser with a Rabi frequency omega and the detuning delta. So if I write down the Hamiltonian for my system, this is written here. I have the laser driving part here and the van der Waals interaction. If atoms I and J are both in the Rydberg state, then they will interact via this van der Waals shift here. And so I need to have the atoms in the Rydberg level. So that's why I have this projector here, Ni. And if I rewrite this in terms of the spin matrices, basically this involves this sigma z term. So in this interaction term here, you get sigma zi, sigma zj term. So this is exactly an Ising type of spin-spin interaction. And the laser driving, you can see it as an external magnetic field for your spins. The Rabi frequency plays the role of the transverse field, and the detuning plays the role of the longitudinal field. All right, so when you have this kind of Hamiltonian, one of the things you can think of is, for instance, to try and prepare an interesting ground state like an antiferromagnet for your system. So what we can do is choose the lattice spacing of our array. We can choose the principal quantum number and the Rabi frequency and so on, such that the blockade radius is comparable, slightly bigger than the lattice spacing. And then what happens is that if you excite a Rydberg level, Rydberg atom here, for instance, you will prevent the excitation on the nearest neighbors, but you can have the next nearest neighbors still excited to a Rydberg state. And so you expect that for the appropriate detuning, the ground state of this system is this antiferromagnet. And of course, if you have an even number of atoms in each side, this would be there would be two different states that are equivalent. So how to do that? The idea is to do some kind of adiabatic preparation. So this is a sketch of the phase diagram for this system as a function of the laser parameters, so the detuning here and the Rabi frequency. And you've got this antiferromagnetic phase here within this dome. And outside of that, you've got just a paramagnetic phase where your spins just align with the external magnetic field, which is given by your laser. And so if you are at negative detuning, the ground state here is all the atoms in the ground state. So this is exactly the starting point of our experiments. And now the idea will be just to navigate through this phase diagram by varying simultaneously the Rabi frequency and the detuning, such that if you are slow enough, you may end up here in this antiferromagnetic ground state. So, and you see that this detuning here acts a little bit as a kind of chemical potential, and you can control the magnetization of your system if you wish. So, of course, there were previous experiments studying this kind of system, and of course, you all know this beautiful experiment 2 years ago by the Harvard group, where they did this 1D chain with this beautiful ordering of the Rydberg atoms. And in our case, we also did roughly at the same time experiments in 2 dimensions, but at the time we had relatively tiny systems like 36 atoms. And if we measured, for example, the spin-spin correlation function after doing this kind of adiabatic sweeps, this is what we got. So you see that we see nicely this change of sign alternating from one neighbor to the next for the spins. But so this is what you expect for antiferromagnetic correlations. But of course, you see that the contrast of those correlations decays very fast. And if you fit an exponential decay to this, you get a correlation length, which is pretty small. It was like 1.5 lattice spacing. And at the time, we could understand that the limitation of that was due to the driving. Our driving of the ground to Rydberg transition was not coherent enough to have very long correlation lengths. And so this is what we had at the time. So the kind of Rabi oscillations between the ground and Rydberg state that we had. And the reason for that is actually, there are several reasons, but one of them is that we were using the intermediate state 5P, where you have a relatively strong spontaneous emission. And also, we're using laser diodes, which have a relatively strong phase noise around 1 or 2 megahertz. And so once we understood that this was really the limitation, we changed our laser system to something more expensive, but better, which is this excitation via the 6P level, which has 5 times less spontaneous emission. And these are TISAF lasers, which have very low phase noise at high frequency. And this is the kind of Rabi oscillation we get. This is the same I was showing before. And so this is much better. So the hope was to have also some improvements in the preparation of these antiferromagnetic states. And so this is exactly what the students did in the lab just after lockdown in summer and so on. And they worked pretty hard together also with Andreas Leuchli, who supports us from the theory side, and they did very nice and heavy simulations to really see what could limit our results and so on. So this is what I want to resolve. So we've put this on the archive at the end of last year and simultaneously with the Harvard group. Okay, so we started by redoing exactly the same kind of experiment as before. So just a small 6x6 square array. And of course, the idea is that in the lab, you just repeat many times the experiment and you just see the kind of outcomes that you get. And what's really cool is that in the lab, you get very often this perfect antiferromagnetic ordering. So here it's a histogram of the states that you get when you repeat the experiment. In principle, you have 2 to the 36 possible outcomes. So this is 70 billion. But still, very often, like 10% of the time, you get either one or the other antiferromagnetic states. So this is of course very nice, and all the more that in fact when you look carefully and you analyze this this sort of noise here, actually you realize that this is due to detection errors. Sometimes we have a Rydberg atom that we mistakenly interpret as a ground state atom, and so on. And so, of course, this changes the state you detect, but so the actual quality of preparation is actually better. And so you can do this on a 6x6, but very quickly you can do this on a bigger array. And in the lab, sometimes you even on such large arrays, you really get on the computer this kind of fluorescence image, which is the final image taken at the end of a sequence, where the atoms that have been excited to a Rydberg level are lost because they are just expelled from the traps. And you see this very nice antiferromagnetic ordering. So, I mean, of course, on such a big system as a 10 by 10, it's kind of a rare event, but it's one shot in 500 or so, which actually is a lot when you try to compare this to 2 to the 100. So, of course, then you want to analyze this a bit more carefully. And one of the things we did together with Andreas Leuschli is to actually do some statistics on the snapshots we get. So I've shown you this perfect ordering here, but this is a more standard, I mean, a kind of typical thing you would get in an experiment. And you see that actually you've got a very large part of the system where you have a very nice antiferromagnetic ordering and then some sort of defects. And so you can actually spot those defects and classify the different snapshots by the size of the largest antiferromagnetic domain that you get. So in this case, for example, you have a pretty large antiferromagnetic domain with 87 atoms in it. And so you can do a histogram of that by repeating the experiment many times. And so these are the blue results. And so you see that actually there is a very strong peak here, very close to 100. What our theory colleagues did was to try and see if you assume that, in fact, this machine is a kind of classical machine, which is just preparing some kind of thermal ensemble. From the measured distribution, you calculate the average energy of your system, because for zero Rabi frequency, it's just something that you can get from the just from the snapshots, and then you calculate what kind of classical distribution you would get. So just with a classical Monte Carlo simulation for the same temperature, and this is what is shown here in yellow. And you see that the distribution that we get is very different. We have a much bigger peak here, close to the ideal case of antiferromagnetic ordering. So I think it's a nice indication that what's happening here is really quantum, even though we don't have a huge doubt, because when you see the nice Rabi oscillations, it has to be coherent, but it's a nice indication at the many-body level, I would say. All right, so of course, then you can calculate your correlation function, and so this is something we did for like a 10 by 10 array, or even for even bigger, like 14 by 14. And our colleagues in Innsbruck were able to actually do some simulations of the actual dynamics of the system with the finite speed of the sweeps and so on, by doing matrix product state simulations. But of course, this is very, very challenging, and they were really pushing the things to the limit. And they were able to do this for 10 by 10. So this is the result of the simulation here. This is in the lower part of the graph. And for 14 by 14, of course, it's totally out of the question to try and do that. But you see that the agreement is actually really pretty good for the 10 by 10. And so this is quite nice, and this brings confidence that what you get for the 14 by 14 is what you should get. All right, and so to compare this in more detail, we did some comparison with what occurs during the dynamics, during the sweeps, And this is shown here. So here what is plotted is the staggered magnetization of your antifold magnet. So you've got the experimental points and the results of the simulations, so those two curves here. So for 6x6, you see that there is a really pretty good agreement without any adjustable parameters, so it's nice. Now, if you go to 10x10, you see that if you do the MPS simulations for the ideal Hamiltonian that you think you program in your machine, there is clearly a discrepancy. And in fact, those simulations allowed us to really point out what the reason is for the discrepancy, what they had to put in the simulation. So the simulations are purely unitary. There is no dephasing, no nothing. What they had to put was the slight positional disorder of our atoms, which is due to finite temperature. So you've got your atoms which do not sit exactly at the minimum of your optical tweezers. And so from shot to shot, the actual configuration that you do during your quantum simulation is not exactly the same. So you have a little bit of disorder, for example, in the interaction strength for your spin-spin interactions. And also we included other small experimental imperfections that we can know and measure, like the fact that we have finite beams for Rydberg excitation and so on. And then you see that the agreement is actually much, much better, even on this 10x10. So this is really a nice way for us experimentalists to know where to put the effort in the future. All right. So the next thing, of course, we did was to take advantage of the fact that we can really program the geometry of our array. So just by essentially clicking on the mouse button, you can switch from the square lattice to the triangular lattice, which is, of course, kind of interesting because we all learn very early that if you have antifold magnetic interactions in a triangular array of spins, you've got frustration. And even in a classical system, this leads to the fact that you have exponentially many degenerate ground states. So this is this has been known for a very long time. But of course, what's very interesting is what happens when you add your transverse field, and there are interesting phases that should occur, like order by disorder phases and spin liquids and so on. And so we wanted to give a first go at trying to see ordering of antifold magnets on a triangular lattice. So the thing to realize is that, in fact, of course, the triangular lattice is frustrated for the Ising model if you want to have as many spin up as spin downs. But there are some nicely ordered phases on this triangular lattice, which occur at 1/3 and 2/3 fillings. So, for example, if you have, so basically a triangular lattice is a tripartite lattice. So you have sublattices A, B, and C. And if you are at the appropriate detuning, you have nice ordered phases with long-range order, with Rydberg atoms populating, or spin-ups populating only the sites of sublattice A, for instance, or sublattice B or C. And then if you increase the number of the magnetization, so to say, you get the same kind of phases, but where you replace spin down by spin up. And so one thing that we just wanted to investigate in the first place was, are we able to observe these kind of ordered phases before trying to observe things which are more difficult to observe, which are, for example, these order by disorder phases that occur here just in the middle of those two lobes. And so we did experiments with this kind of shapes of arrays. So this is a triangular lattice. The patch here is a kind of hexagon, and maybe you can see that it's not actually a nice regular hexagon. And the reason for that is that actually to observe nicely this ordering on the triangular lattice, what you want to do is to have as many sites of sublattice A, sublattice B, sublattice C. And so the way we build those things is to, you start from a central triangle and then you add layer by layer, those extra layers, and so in the end you get to have exactly as many sites of type A, B, and C. So I think and it turns out this is really important if you want to really see on those systems with the finite size effect and so on to see those kind of ordering. Having the control of the geometry at a level where you really control exactly the number of atoms actually is quite crucial. So this is something which is, I think, a big asset of the Rydberg platform. And so if you take this kind of array and do the same kind of sweeps, then of course you will get many snapshots, you repeat the experiment and so on. And one way to plot the results is to plot what we call sublattice histograms. So you just count in your lattice, in your snapshot at the end, how many Rydberg atoms are on the sublattice A, on the sublattice B, and on the sublattice C. And you just construct this complex number. And so basically, all the points will lie in a hexagon like this. And for instance, if you are in this 1/3 phase, ideally, if you prepare this without any imperfection and you really prepare the ground state, you would obtain either a point here or there. Because basically, for instance, this corresponds to having all your atoms, all your sites of sublattice A containing Rydberg atoms, and no atoms on B and C, and the same for the other ones. Now, the 2/3 phase, you would get points here on this thing of the hexagon. So now we do the experiment, and this is what we get. So here, the experimental results is the blue thing, and then it's symmetrical with respect to the horizontal line here. And so you see that we do observe very clearly this kind of triangular pattern, even though we do not prepare exactly the perfectly ordered state, but this is something we know even on the square lattice. Huh? Of course, our ramps have a finite speed and so on. But clearly, you see hints of this ordering. And here at the bottom, you've got the results of the matrix product state simulations for the actual ramp that we put in the system and so on. And you see that the agreement is actually really very, very good. Again, there are no adjustable parameters here. It's just taking the known imperfections from the system. And we can do the same. So then we can measure correlation functions, of course. And we can do the same also for this, this 2/3 phase here. And here you see also a triangle, but it's in the opposite direction. Okay, it's pointing towards those blue dots here. You see also that it has a somehow smaller size, and this is expected. Actually, it's something which arises from finite size effect. So for those data, we have 108 atoms, and actually this is, I mean, it's a large system, but still the number of atoms on the edges is not totally negligible, and they do not have as many nearest neighbors as the bulk atoms. And so this is enough to really reduce the size of the ordering. So more generally, I think it shows also that trying to scale up those platforms to very large numbers is something that is really important at some point, because you want to try and get rid of edge effects and so on. And so this is an important motivation also to go to large numbers. All right, so yes, I can stop a bit here, and then probably, if there is time after the questions, now I could briefly give some examples of XY simulations, but
maybe I'll ask two very quick technical questions, and then we can proceed to the end.
Yeah.
The first is from Preston Huft. He asks, how large was the single photon tuning from the intermediate state in each of the two excitation schemes you showed?
So it's very similar, actually. It's on the order of 600 megahertz. I mean, it depends a bit, but yeah, this is around this.
Okay. And Shuyu Sherry Zhang asks, is there some principle to find the adiabatic sweep trajectory to hit the desired phase? Is this done through numerical study? And in general, sort of like, are all states or arbitrary states reachable by this method?
So yes, this is a very, very important point. So I mean, of course, this is a whole industry at the moment to try and find optimal control. I mean, to use optimal control, for example, to shape pulses and so on.
Mm-hmm.
And in our case, what we did was really basic. We did, I don't know if I don't think I showed the actual shape of the pulses, but it's just a linear ramp. So it's piecewise linear, and I mean, essentially in detuning, it's just a linear ramp. And for the Rabi frequency, it's a kind of trapezoidal shape. So we ramp up linearly, we stay at a constant thing, and we ramp down linearly. And so, and the only thing we sort of optimized, but entirely empirically, is the optimum time, the global duration of the pulse. Because of course, if you are too fast, you are way too fast to be adiabatic. So this is bad. If we go very, very slowly, of course, we start to suffer from decoherence and also from losses of the atoms because they start moving too much and so on. So we optimized, but experimentally, just the global duration, and it's typically 6 microseconds. But of course, this is something so the results could presumably be improved by shaping better the pulses. At the same time, very often, if you want to optimize the pulse, in some sense, it's very, I mean, numerically, it's quite, I mean, it's quite expensive in terms of calculations and so on. And I think it's important to, I mean, it's nice if you can improve the results, but in some sense, you also want to have things that are a bit, you know, theory agnostic, if I dare say. I mean, you can just go to the lab, program a ramp and get already some meaningful results. And so this was our approach there.
Okay, and maybe just because it's topical, I'll ask one more question on this section. So Nathan Shine asks, for the 2/3 phase, can you analyze only the bulk atoms and see the triangle reach full contrast?
Well, so I mean, of course, we did lots of things to try and analyze, you know, just the bulk and so on. So it helps a bit, but it's I mean, at some point you also start to suffer from the fact that you have then less statistics and so on. So it's I mean, I think it helps a bit, but it's not like a perfect way to get this perfect contrast. So I think really, if you want to improve the contrast for this kind of thing, what you have to do is to go to larger sizes. Or another approach maybe is to add some local fields to detune the external atoms differently from the atoms from the bulk. So this is something we have not done, but this is something that in simulations it should improve.
Good. Okay. All right, let's keep going here. Thank you. If it runs a little bit over, that's okay too, Thierry.
Okay. So anyway, so I will try to keep brief for this last part. So, but it's just more to advertise this works somehow. So it's just to show that we can also really use this XY spin model I was mentioning for doing some interesting physics. So this is work we do with Hans-Peter Büchler from Stuttgart for the theory part, and we use this XY model to realize synthetic topological matter. So we are just doing the first steps, but we did two works in 2019, 2020 for trying to realize this topological matter. So this XY spin model, we use the resonant dipole-dipole interaction this time. So you use two different Rydberg levels, S and P, for example, and so you encode your spin there, and the resonant dipole-dipole interaction then is really a spin exchange between two atoms. Okay, and so in fact, when two atoms exchange an excitation, it's just mathematically equivalent to having a quantum particle hopping from one side of a lattice to another side. So if I take, for example, just 3 atoms, spin up, spin down, due to the dipole-dipole interaction, those 2 guys can exchange their internal states. So I have down, up, down, and this can go on, of course. So I have down, down, up. And so the spin excitation has moved essentially 3 sides by a kind of hopping. Okay, and so this is something, it's just a perfectly rigorous mapping onto this model. What's interesting to think of is now imagine you have 2 spin excitations on 2 neighboring atoms. Of course, then you cannot have this spin excitation hopping on the other atoms. So in terms of these particles hopping in a lattice, you've got a system of hardcore bosons. You've got particles that can hop around, but of course, you cannot have 2 bosons on the same side. And so this is something which is pretty nice because basically it's relatively easy to, if you set up a lattice and play with the number of excitations in your system, you can really go from a single excitation regime, so single particle physics, to a system where you have very strong effects of the interaction because you have this hardcore constraint. And so we did, we used that in this work here to study the Su-Schrieffer-Heger model, which is basically the simplest textbook-like example of topological system, but using those hardcore bosons. And so we could use our ability to tune the geometry of the system and so on to observe, single particle physics. So for example, the fact that depending on how you prepare your system, you have either a trivial state or a topological state with some edge states that you can observe by microwave spectroscopy. But this is single particle physics, so it's something that you can actually simulate even with electronic components or mechanical oscillators. But with the same system, just by now driving the system with microwaves and introducing many spin excitations in the system, you can fill fully the lower bound of your system, and you end up in a new phase, which is called the symmetry-protected topological phase, where the topological properties of the system are not governed by the same symmetries as in the case of the single particle system. So this is really a many-body topological phase, if you wish. And so this is something that we could really do with this platform, which I think is kind of hard to do with for example, with ultra cold atoms in optical lattices, because when you put numbers, it's kind of hard to have such strong interactions. So I have no time to go into the details because I mean I would need at least half an hour to get you through all the details. But this is also a nice feature of this platform. And so the next step, of course, is to go to 2 dimensions, because this is a bit more interesting for topology, because you don't need to have a symmetry to protect your topological phase. You can have intrinsic, robust topological order. And so to do that, following a suggestion by Hans-Peter Büchler, we did a demonstration that you can use this dipole-dipole interaction in a slightly more complicated manner to introduce spin orbit coupling for your hardcore bosons. So it works this way. So now you will use still the resonant dipole-dipole interaction between your Rydberg levels, but you will use 3 different internal states of the Rydberg atoms. So if I take 2 atoms, I and J, I have, for example, the S state, so I will call it 0, and I will use 2 different Zeeman sublevels of the P state. So I will call them minus and plus. So here they are. And so assume that the first atom is in minus, the other one is in 0. Then the dipole-dipole interaction can induce a process where this guy goes down, this guy goes up, and so you end up exchanging the spin excitation, the minus excitation between the two atoms. So this is exactly the hopping process that I was mentioning before. But the dipole-dipole interaction also allows this guy to go down and this guy to go up to the p state, but to a different Zeeman sublevels, because you don't have to really conserve angular momentum, the spin angular momentum. So this process is allowed. And when you write down the Hamiltonian for the system, you see that actually the matrix element has a complex phase here, which arises just from the geometry, the geometrical arrangement of your atoms. And so this, you can see it as a particle which hops from a site to another, but which has an internal degree of freedom. It can be minus or plus, and it can just hop with a real matrix element staying a minus particle, but it can also hop and change its internal state and acquire a phase, an orbital phase here. So this is exactly a spin-orbit coupling. And so we demonstrated this in a minimalistic setting of just 3 atoms. So we have those 3 atoms in a triangle here, and we prepare the system initially on the blue atom here. So we put a minus excitation here, and we just let the system evolve and see where the center of mass of this minus excitation is going. And when you do that, you see that actually it's moving, but in a preferential direction. It's going towards the red atom, and then from the red to the yellow, and then back, and so on. And so you have this chiral motion of your spin excitation. And this is really what you expect exactly from this spin orbit coupling. And so what's very interesting with this platform is that you have this hardcore constraint for your spin excitations. And so now, for instance, if you are doing this, and this has been done, for example, with superconducting qubits, you do this experiment, you observe this chiral motion, and now if you put 2 excitations, actually you would observe still a chiral motion of the hole that you have in there, with, for example, with superconducting qubits, because you don't have this constraint of hardcore bosons. But with the constraint, in fact, what happens is that if you put 2 particles, the chiral motion stops, and you got a symmetric hopping of the hole between the 3 atoms. So again, I have no time to go into all the details, but so this is a very simple proof of principle experiment with just 3 atoms. There is no many physics there. But it's a nice step towards trying to do this on much larger arrays in 2D. And we hope, and Hans-Peter is doing some simulations, that this is something we can extend to first observing single particle physics in large arrays like edge currents and so on. But it's also trying to reach a many-body regime where you expect fractional bosonic topological insulators and things like this. So this is very complicated, and it's not entirely clear how you prove that in the lab and what you should measure and so on. But I think it's very exciting for the future. All right, so I'm done. Sorry for being a bit too long. And maybe one final thing. Sorry. So I hope I have convinced you that these Rydberg array are nice platforms for simulation of spin models. I think in the future, it's realistic to say that we may scale that up to maybe 1,000 spins or so. And also, so this is something we are not pursuing in our group, but very recently there were really exciting news from Harvard, from Caltech, about achieving very nice fidelities for quantum gates with these systems. So this is also something very nice. And as you know, now this is an adventure which goes outside also the academic realm. There are some companies that are being started to try and make those machines accessible for customers actually. And I'm lucky enough to be involved in one of them. So it's called Pascal, and it's started a bit more than 1 year ago, and the idea is to try and build a machine where you can have this Rydberg quantum simulator available either online or in HPC centers. And so this is a mock-up of the thing, but this is the first prototype which is being built at the moment at Institut d'Optique. And with that, I would like to thank you for your attention. And again, I apologize for being a bit too long.
Great, thank you so much. Sorry, I was having trouble finding my unmute button. All right, we have a couple of questions here, and then maybe I'll defer remaining questions to the post-Vamos discussion, just in the interest of time. The first question comes from John Simon. He asks, do you have ideas for tailoring the spatial form of the interactions? For instance, they could be sign changing or otherwise oscillating interactions in space.
So it's a good question. So for changing the sign or having oscillations, I don't think it's really, I mean, I have no clear idea of how you would do that apart from other approaches like dressing and so on, but which have their drawbacks, of course. Probably if you want to have oscillating interactions, then you could think of using the resonant dipole-dipole interaction, but with an optical transition. But I mean, then of course it's a bit different. In terms of changing a bit the type of interactions we want to have, one of the things, so it's a bit unrelated, but there are some ways, for example, of extending a bit the type of spin Hamiltonians you can have. So for example, you are not necessarily restricted to Ising or XY. You could, there are ways to go to Heisenberg models or like XXZ models, and you can do this either with a 1/r³ or 1/r⁶ behavior. So we can expand a bit the type of interactions, but then if you want to do some things which are really exotic, I'm not sure it will be that easy. Maybe it's possible to find some schemes, but then it's probably sort of a lot of engineering, and then how reliable the thing is, it's not entirely clear. So, but yeah, I don't know.
Got it. And let me ask just one more question here. So this is from Anupam Mitra. She asks, is there a difference in the effect of inhomogeneities, for example, due to atomic temperature, in the case of a square lattice versus a triangular lattice?
So, essentially the strength of the inhomogeneities and so on, essentially it's comparable. But of course, then the effect might actually be very different, because especially if we want to prepare, I mean, this is work in progress with our colleagues in Innsbruck. So we have, I think, nicely demonstrated this 1/3 and 2/3 phase for the triangle. But of course, the most exciting part is to go just in between those two lobes, and to try and observe these kind of spin liquids or you know, order by disorder phases. And if you want to do that, it seems it's actually these phases, which are a bit exotic and so on, they are very, very sensitive to any kind of little disorder and so on. So I think the answer is yes. Depending on the kind of phase you are shooting for, the requirements on the quality of your simulator in terms of disorder and stuff like that, they change. That's for sure. And so it's good news for us experimentalists, because it means we have to improve the platform even more. So,
got it. Cool. Great. Well, thank you. Would you mind unsharing your screen for just a moment so I can
show our
slide? All right. So interesting. Can you see this? Yeah. Good. Okay. So just briefly, we have upcoming talks here. So at the Quantum Sciences seminar series, Dieter Jagsch will be speaking from Oxford. That's on Thursday. And then at Vamos next week, we'll have Cater Merch from University of Washington, St. Louis. And that'll be at the usual time next Friday. Great, thank you so much. I think the link should be in the chat for the post-Vamos discussion. Hopefully see some of you there.